Welcome. This is Azad Academy, a place where you can learn about topics in machine learning, deep learning, and artificial intelligence. Latent space representation, a hands-on tutorial on autoencoders in Tensorflow. This is a part 1 of the series of tutorials on unsupervised learning using deep neural networks. This would cover the following topics: autoencoders, variational autoencoders, generative adversarial networks. In this tutorial, the focus would be on latent space implementation using autoencoder architecture and its visualization using t-SNE embedding. Before we delve into code, let's define some important concepts, which we will encounter throughout the tutorial. The real-world data is often redundant and has high number of dimensions. This poses challenges not only for the computational efficiency but also hinders the modeling of the representation. Consider, for example, the Swiss roll in this figure. The data is in 3 dimensions. However, when we unroll it, it only required 2 dimensions to represent the same object. This is called dimensionality reduction, more specifically, dimensionality reduction using manifold learning. The basic assumption here is that the high-dimensional data has often a lower dimension embedding, which is sufficient to represent the content of the original data. Now, if we extend this concept in image representation problem, we realize that there must exist a lower dimension space that should be sufficient to describe the content of a given image data set. We call such space as latent space. It is a lower dimensional manifold of the high-dimensional images where we expect all the instances of the data set to lie in proximity. Autoencoders. Now that we know what a latent space is, let's dive into the concept of autoencoder. Usually, when we intend to build a machine learning model, we train the model on a sequence of images with the given labels and minimize the loss function, which quantifies the mistakes made by the model. This is called supervised learning, whereby we provide the algorithm with labels for each instance. However, in real-world applications, often these labels are missing, or we want to extract the inherent structure of the data set. For example, the relationship of data set instances with each other. This requires a different approach called unsupervised learning. Autoencoder is one of such unsupervised learning method. It embeds the inherent structure of the data set by projecting each instance into a latent space whereby the similar objects or images tend to lie in proximity. A general architecture of an autoencoder is shown here in this figure. A typical autoencoder consists of 3 parts: an encoder, a latent vector, and a decoder. The input image is first projected into the latent space by encoding layers of the network, resulting in a latent vector in a lower dimension than the original image. This latent vector is then used by the decoding layers of the network to reconstruct the original image. The training objective of the autoencoder model is then to minimize the loss between the input and the reconstructed image. The final latent space vector obtained after convergence is the embedding of the image into the latent space. Now that we have understood the concept, let's implement an image autoencoder in Python. In this tutorial, we will build an autoencoder from scratch using Tensorflow, and then apply it on a fashion objects database. You will find the link in the video description below. This tutorial will require Tensorflow 2.0 and Jupyter Notebook installed, so if you haven't had it set up already, you can either use Google Colab or set it up on your computer using Anaconda. We will start by importing the prerequisites in the Jupyter Notebook, and then we will load the data using Tensorflow's data loader. Then we will pre-process the data set by resizing and normalizing the images. Here, we first load all the images from the directory at dbpath using the Tensorflow's built-in function. Then we split the data into training and test sets. Now we prepare the images for the model. by resizing and normalizing them. This is achieved by mapping the load image train function onto the Tensorflow dataset object, which then applies the processing on the individual images in the respective dataset. We also shuffle and prepare the batches of the data, ready for training. Once the data has been loaded and processed, we can visualize the data. This can be done by Python's matplotlib library. Now that the images have been successfully loaded, it may be interesting to see how they cluster together in hyperspace. Since we don't know any labels, it would not be possible to draw a scatter plot of the various objects. However, we could try to visualize the data by embedding the images into a lower dimension space and then visualizing the clusters. This can be done by a principal component analysis embedding. PCA is similar to a latent space embedding, however, it is a linear model. We can see from the embedding that although PCA formed clusters of objects, but it failed to capture the inherent structure of the data set. We will do the same with the latent space in a moment and see the difference. Now we build the model of an autoencoder. We start by adding the necessary imports from Tensorflow library. We import the layers, models, and optimizers from keras package of Tensorflow. We start with an input layer of image size 60 by 60 by 3 and then add a convolution and a downsampling layer. We then add a set of convolution layers. Each convolution layer is followed by a downsampling layer which reduces the size of the image by half. First parameter of the TOAD convolution function specifies the number of kernels learned at that layer. Number of kernels learned are reduced as we move down the network. After 4 convolution layers, when the image size reduces to 3 dimensions, we flatten the output and add a fully connected set of layers. Then we direct the output to a latent layer called Z, which is also the output of the encoder. The encoder looks something like this. Pause the video for a while and see if you understand the output and how it relates to the code. We then build the decoder layers by following the similar process as we did with encoder. The decoder starts with the latent vector as an input and gradually reconstructs the original image. The input is reshaped into 2D after a couple of dense layers. These dense layers are where the weights are trained and the learning happens. The reshaped output after the dense layer block is then followed by a set of inverse convolution layers. Each inverse convolution layer is followed by an upsampling layer which doubles the size of an input image. The inverse convolutions and the upsamplings continue until we achieve an image of the original size. The layers of the decoder look something like this. Go ahead and pause the video. See if you can understand it and how it relates to the code. We can obtain the complete autoencoder by joining the encoder and the decoder layers. We can do this by chaining the input layer of the decoder with the last layer of the encoder. The full autoencoder looks something like this. Pause the video and see if you can understand how it relates to the both encoder and decoder layer blocks. Now that we have built our autoencoder model, it is time to train the model. We use Tensorflow's optimization functions to achieve this task. The fit function takes as an input a training data set, a validation data set, and a number of epochs to train. We pass it our preprocessed fashion image data set and train it for 10 epochs. Each epoch contains a number of training steps depending on the size of the data set. At each training step, a random batch of images is sampled from the data set and gradient descent step is applied by computing the loss and updating the weights. As we did with the PCA embeddings earlier, we project images into an hyperspace. However, this time we use the trained encoder model to achieve this task. The output latent vectors are then plotted using TSNE embedding, which further reduces the dimensions to 2 dimensions for visualization. This concludes the tutorial. In this you have learned about the autoencoder models. You have also learned how to use Tensorflow to load and process image data sets. Then you have learned how to construct an autoencoder model in Python. You have also learned how to train an autoencoder and how to visualize a latent space. You can practice the learning using Jupyter Notebook. The link to the GitHub repository is in the video description. Thanks for watching the video. I hope that you have learned the concepts in this video and it would improve your understanding and knowledge. Feel free to post your question in the comments section below.